this is where we left off last class, and we were talking about longitudinal shear stresses, right? So basically, if I have some beam loaded, we all know that if we just that force right there is gonna want to shear the beam, right down that portion of the beam. But we're gonna have shear stresses acting on this cross section of the beam. But also what we talked about for longitudinal or transverse shear stress, we're going to have shear stresses acting along the length of the beam, on a plane along that length of the beam, right? So that's what we tried to calculate the last time using the shear stress, longitudinal shear stress equals VQ over IT. All right, so one of the first things I want to do today is let us I'm just going to add a page to longitudinal shear stress here. And we're going to talk about shear stress on an arbitrary, I think that's how you spell it, shape. Right, so for today, basically, we want to be able to explain the variation of the shear stress on that arbitrary shape beam. And hopefully go through some calculations on how to calculate shear stress on an arbitrary shaped beam or maybe a box beam as well. So here goes. All right, so draw. Let's start with shear stress on an arbitrary shape. So let me draw this beam. Right, and let's say the cross section, since we're talking about arbitrary shape, let's say the cross section for this beam looks like this. Right, the neutral axis is probably going to be closer to the bottom since there's more mass at the bottom. All right, so that will be my neutral axis. And we talked about the shear force delta H from, let's go back and see if I have it here. And of course, for some reason it's gone. But we talked about delta H, right? That force, put it at the bottom. That shear force at the bottom, the longitudinal shear force, right? So therefore, that delta H, that force, is going to be equal to VQ over I delta X. That's what we determined in the last class. And then the shear stress was VQ over IT because we divided this by the area, delta H over the area, which is the thickness times delta X, right? And then we're going to end up with VQ over IT. But the force itself is VQ over I delta X. And just for you guys, go back. Right, delta X is just the distance going from C to D, right? So that's your delta X for just a small part of that beam, right? So if I do delta X, delta H here over delta X, basically I'm just simplifying this equation. That is VQ over I. And we usually call this term VQ over IQ, which is just a horizontal shear per unit length. Right, so I'm going to write that in red. Horizontal shear per unit length. Right, and again, it's just delta H over delta X. So horizontal shear, delta H over delta X per unit length. Right? Generally, you might see that term somewhere listed as Q. So, and of course, I'll go ahead and just do this again, but you all know shear stress is delta H over the area. So therefore, delta H over T delta X. So therefore, we ended up with VQ over IT, right? And for arbitrary shapes, T may change. Let me circle T. Right? T may change, and let me put that here for arbitrary. Right? So depending on, right? So if this is my cross section, depending on where on the cross section, if I'm here, 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 as y'all can see, the thickness, right, would change depending on what part of the height of the cross section that we want to calculate shear. So therefore, T should change for arbitrary shapes, right? So let's see. We're gonna try to work maybe an example problem. Let me just. Let's just say example one. So for example, joint box. All right. All right. So we have a square box beam, and the cross section of that beam. Let's see, black. So if I have a beam like that, and it's a wooden box beam. So here's the top section, and that's nailed into the side wall here. I need to make that longer because now we got another bottom here. So that wall goes down to here. Right, so you have this bottom section and this top section, and they're nailed in. So if you want to say maybe there's a nail here and that nail goes through, a nail here and that nail goes through, and similarly from the bottom we have a nail that goes through here. So maybe at different sections. So this is a little different than the glued section that we've talked about, right? The glued section, you're going to have bond between along the entire length where the glue is. But for the nailed section, you really just have the bond at that nail section, right? Or you're going to have resistance for that plank to move up. The nail is going to try to resist that. So what we're going to do is we're going to say, for example, this nail is going to actually take on resistance from this portion to that portion, right? And then this nail is going to take that resistance from this portion to the next portion over, right? So that's kind of the idea here. So we have this box beam, and let me put some dimensions on here. Let's say, let's just call this spacing S for now, between the nails. And we have 20 millimeter planks and 80 millimeter on the wall, millimeters, and 20 millimeter on the plank at the bottom. Right, and let's say the plank at the bottom and top is 120 millimeters. Right, so the box beam, that's the box beam. We're going to say S is equal to 30 millimeters. And we're going to have a vertical shear, V, is going to be equal to 1,200 newtons. And we want to find A is the shear force in each nail. And B, the maximum shear stress. So let me say max shear stress. in the beam. All right. So, what are the first things that you think we need to do? Right, we're trying to find shear force in each nail. So, how do you think? Does anybody want to maybe kind of tell me how can we get there, or what's one of the things that we need to do? One of the first things that we might need.
Free body diagram.
Right, you remember? Say again.
A free body diagram.
We could draw a free body diagram, right? But we're already given the shear force, right? 1,200 newtons. So we can really skip that portion. But then if you remember the equation for shear stress, right? Shear stress is going to be VQ over IT. So we have V, right? So we need I, we need Q, and of course that thickness, we can talk about the thickness here in a little while, right? So that's the idea. I just kind of wanted you all to try to picture that. Just think about the equation. If you're looking for shear stress, right? But the first thing that actually they ask us to do is shear force. So basically that's that delta H, right? But we're still going to need I. We're still going to need Q. So let's try to see if we can determine I for this cross section here. I would be equal to, anybody want to tell me how can I calculate I for a hollow section like that?
Is it 1/12 base height cubed minus the smaller portion inside?
Exactly. So it would be 112 BH cubed. Let's call the outer one, right? Or let's call it 2. And then we call the inner portion 1. So B1 H1 cubed. Right? We just subtract that inner portion, the moment of inertia from that inner portion. Right? So therefore, we're going to have 112, 120, 120. It's a square beam minus 112, and the inner portion is 80 by 80, so 80 cubed. And you should end up with a factor for moment of inertia of 13.86. Just put it on here, 667 times 10 to the 6 millimeters to the 4th power. Right, so we have I. It was easy to cancel because we got a rectangular beam. So let's try to see if we can determine Q. Right, Q is the area times that y distance. Right, what is that y distance that I'm talking about?
Would it be the heads of the nails?
Right. So we're looking at shear stress, right? And if this plank is going to pull up, we want to look at shear stress or shear force, right? And again, remember, it's horizontal. It's a horizontal shear force. So basically, we're worried about. Let me put that in red. This section right here pulling out, right? The shear force within the plank at the bottom, right? So we're worried about this section pulling out, right? So if we're worried about this section pulling out and we have a neutral axis, right? So this is our neutral axis, right? And we want to determine Q above or below that section. So let's say we want to determine Q above because it seems like it'd be easier. So that's the area that we need to worry about. And therefore we need to go to the centroid of that area. So therefore this is my Y. right? You go from the neutral axis to the centroid of the area that's in question, right? And Q again can be below the area below or above the neutral axis, or the point in question of where you want to calculate shear stress or shear force. All right, everybody okay with that? I hope.
Yeah.
Yes.
All right, good deal. All right, so Q is the area times that y distance. I'll call it y tilde here. So therefore my area is 120 by 20. This is millimeters by 20 millimeters. And let's see, what's y? Y would be, so if this is to the centroid, this is 40 to here, and this would be 10, right? So that's 50. 50 millimeters. Right, so my Q should be 120 times 10 to the 6, and times 10 to the 3, right? Millimeters, Q. All right, so if I go ahead and determine Q, we talked about Q, and Q is that horizontal shear per unit length, right? And the first part of the question was asking us for the shear force, right? So that horizontal shear force per unit length. So let's look at Q. Q, we know the equation is VQ over I or delta H over X, right? But we know V, we know Q, we know I, so we can quickly calculate that shear force per unit length. You know, V is 1,200 newtons. Q, we just calculated as 120. Let's see. We should put that in meters. So we're going to end up in Newton per meter. That's kind of where I'm trying to go here. So if I put that in meters, I think that should be times 10 to the minus 6 meter cubed. And that's Q. And I, we have as 13.866 times 10 to the 6. That's millimeters to the 4. So if I want to put that in meters, that should come out to the same 13.8667 times 10 to the minus 6 meters to the 4. Right? So, okay, I have that in meters. And y'all can do this in millimeters. I just wanted to change it to meters. So therefore, we're going to have Q equals 10.3846 times 10 to the 3 Newton per meter. All right, but that's Q, right? So Q is shear force per unit length, right? Shear force, horizontal shear force per unit length. All right, so for every unit length. But remember, if we go back to our beam, we have these nails, and we're saying we're going to consider that these nails can help resist the movement of that board, but basically as large as the spacing of the nails. So again, remember when I said this nail is going to take on midpoint between these nails on this side and midpoint between these nails on this side. So therefore, this nail is going to take on the resistance from this point to the next point up to somewhere up there. Right? So basically, if I go midpoint to this side, midpoint to that side, basically that is the spacing S. Right? So in essence, if I multiply Q by S, right? So what I'm saying is that Q is the shear force per unit length, and each of those nails are resisting the shear force based on that spacing, right? I can write that Q times S is equal to 2 times the force in each nail. Why 2?
Maybe for each side of that.
Exactly, yes.
Yeah.
For each side, right? Because I have 2 nails, right? So basically, I'm now saying Q times S, which is what I'm trying to resist, and I'm doing it horizontally, but there's 2 nails, one on this side, one on this side. So 2 times that force in each nail, basically going to give me Q times S, right? So that's the only reason we have 2 there, because we have 2 nails along that part of the board. All right, so therefore I can write F, the force in each nail is going to be QS over 2, and therefore I should end up with 10.343846 times 10 to the 3. Our spacing was 30 millimeters, so that should be 30 times 10 to the minus 3 meters over 2. All right, so I think if we actually go through this, we should get F nail equals 155.8 meters. Right, so basically what we did differently here, we were looking to calculate shear force, not shear stress. Right, so we used Q, which is the shear force per unit length, and we know that's equal to VQ over I, right? And we try to equate that to the nails, and we know the nails is going to try to resist on either side of them the distance of the spacing of the nails, right? So we use that knowledge and try to calculate the shear force for each nail, right? And if we want to quickly do B, calculate the max shear stress in the beam, where would the max shear stress occur? So I want to calculate maximum shear stress. Anybody want to tell me where the maximum shear stress might occur in the beam?
It'll be near the neutral axis.
It'll be at the neutral axis, right? We know the distribution of shear stress, and we draw it here. Distribution of shear stress is 0 at the extremes and a maximum, right, at the neutral axis. If we have a uniform, like a rectangular square beam, right? So at the, well, even if we don't have a uniform or square beam, say for example, we had this cross section and the neutral axis was a little lower, the distribution of the stress, right, here, between here, is going to be 0 here, 0 here, still going to be maximum at the neutral axis, right? So it's always maximum at the neutral axis, so it's going to be maximum all the way to here and then back down to here, right? Because Q is maximum at the neutral axis, right? All right, so we need to calculate Q, right? Again, shear stress is VQ over IT, so we need to calculate Q because Q is going to change, right? V is not going to change, I is not going to change, and then we need to figure out what the thickness is at the neutral axis, right? So let's quickly look at Q. Let's see. Let me draw the box beam here. We have that box beam. Right? That's what our box beam looks like. We want to be at the neutral axis. Right? So we want to consider for Q, we want to consider the area above or below that point. So the neutral axis. So my area is all of this, right? So if my area is all of this, then therefore I need to figure out what that area is. Let's go back to the box theme. Let's see. So we have 80 and 20. I don't know how I lose some of the writing, but that's 20. So just to kind of help us here, this is 40, and that's 20. That's millimeters. All right, so my Q, excuse me, I think I am going to probably divide this up. So maybe we do this. We use red when we can see it. So let's call this area my first area, right? And then I do this as my second area and just multiply by 2. All right. So with that said, for that top area is 120. So this was 120, I believe. So 120 by 20, that's the area. We're going to multiply by y, so it'll be this distance, right, which would be 40 and 10, 50. That's all in millimeters. Then we need to add this area. So I'm going to say 2 times because there's 2 of them. But the area is 40 by 20, right? And what's my distance to the centroid of that area?
Is it 20?
Exactly. So the centroid of this area would just be right at the center right there. So that distance there. So this is y for 1, or 1, and this is y 2. And so therefore that should be 20. Right? And if you go through that calculation, you should end up with 152 times 10 to the 3 millimeters to the third. Right? So I can now look at my shear force, or maximum shear force, equals VQ over IT, 1200, that's newtons. Q I just calculated as 152 times 10 to the 3, so that's times 10 to the minus 6 meters cube, which is what we did earlier. And I stays the same, so that's 13.8667. I believe it was times 10 to the minus 6 as well. Yes, minus 6 meters to the 4. Times 10 to the minus 6 meters to the 4. And thickness. What is my thickness? Who wants to take a shot at trying to get the thickness? We're looking at the neutral axis, right? We calculate the maximum shear stress, so that occurs at the neutral axis. What thickness should I use?
$40 millimeters.
40 millimeters, right? So I'm going to write it as 2 times 20 millimeters, right? So 20 times 10 to the minus 3, which would be in meters. I should put meters there.
Do you mind explaining that real quick?
All right, so here's the thickness, right? So there's nothing here, right?
Right.
It's an open beam, right? So the thickness that I need to worry about is this distance and this distance,
Okay, got it.
right? So yeah, so that's basically what I'm saying the beam is going to try to pull apart because we got the maximum shear stress. So if I put that beam in bending, most likely it's probably going to break. If I take it a failure, it's probably going to break right along the length of that beam, right at the neutral axis, right?
Okay.
So the thickness that's resisting that stress is these two areas, these two distances, right? So 20 millimeters for each one, so 2 times 20 millimeters, or 2 times 20 to the times 10 to the minus 3 meters, right? And therefore, we should end up with the maximum shear stress 329 times 10 to the 3 Newton per meter squared, or kilopascals. Same thing. All right. So that's the one problem I was wanting us to go through today. But there's one thing else I want to try to get by you guys, and so let's kind of talk. Well, let me ask any questions though regarding what I just showed you.
Not yet. I think I'll just have to kind of look back over these and just kind of interpret it myself.
Yeah, right, exactly. And again, as soon as you all get questions, let me know. But here's what I want to get. So this is the end of the example problem, right? But here's what I want to kind of talk about as well before we have to finish here. What if that box beam what if the planks were this way? Right? Remember, we have on our beam, we had a horizontal top plank and a bottom plank that covered the whole, and just there's 2 walls on between those planks. But this time, my vertical planks, go all the way to the top, right? So if I'm going to nail this, I'm going to have that nail here, which is there, and that nail is going to go all the way to this way, right? If this thing is going to come apart, the shear force that I need to worry about is actually on a vertical face, right? Not on a horizontal face, right? So if you think about, maybe if I can draw just a box here, right? Some kind of soil element. Let's just look at a soil element here, right? If I have, we know now that, of course, if this is some kind of soil element or beam, right, and that beam shears right down where it was loaded, we're going to have some kind of shear force right here, right? We all know that the shear force over the area. That's a simple calculation for shear stress, right? But we're going to have a shear force like that. But what we've talked about is we also have some horizontal shear force acting on that beam, right? But now what I'm trying to say is we also would have a shear force on a vertical face trying to rip this beam apart, right? So we also would have shear force on a vertical face, right? So if we have that, we probably need to figure out this area on that vertical face, right? So now we're looking at the area or the shear force that's acting on that vertical face. But on our cross section, how do we calculate Q? What you see what I'm saying? It's kind of different, right? So we got to understand how the force kind of flows, right? So what I want to present is some kind of a flow diagram. If you have a beam such as this, I should use black. Right, and we have some box beam that we're worried about, right? General flow of that force, or what you might want to consider area is, let's just start at the top. If we start at the top, our force flow is going to be that direction, down, down, and we're starting at the top. So we're going to go out this direction, down, and down, down, and back here. So that's the general way we're going to consider flow of that force, right? So for this scenario here, if I want to consider this area, right, my area in consideration, again, would just be this area between from the start to that point. Right? So that's how you would look at the area. Depending on where you are on your beam, you would look at that area to the point in question, but based on your flow. And here's how it might be slightly different again, but let's look at an I-beam section. Right? If we have an I-beam, our flow usually goes from outside in and down. And usually, if usually what they say is they go from this side down, down, down. I don't think, and then out this way. I don't think it really matters to you guys. And then this one goes this way, and then down, 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 and then back this way. I think what you'll need to know is the flow would go from the outside down and then back outside, right? So if I was worried about a point, a vertical face, maybe here, right? If that's the point that I'm worried about my shear force on a vertical face, again, the area would be, right, either on one side or the other side. So for ease of calculation, I'm gonna just take this side. So this would be my area, and therefore that's the area I need to consider. So does that kind of make sense? Right. So if I'm really looking at this beam, I guess. So let me just show just that portion that I showed the area for, and I'm gonna maybe flip it, and it's gonna probably run that way, right? So my shear force is really acting on that vertical face, right? I know previously yesterday we talked about the horizontal face, and the first question we did this morning was a horizontal longitudinal force. But I also wanted to point out that we also got a vertical force in play, and we can actually consider those vertical forces as well. And I think this picture paints a really good picture of it. If you have a vertical board and a vertical board, and these boards are interior, and you got a nail going across, you're going to have that vertical face that the shear force is acting on. All right, so any questions?
Is that dependent on where the force load is? Would it have to be coming down on that shape?
It's possible. It's possible you could have a load right here, but the idea is if the load is anywhere here, if you just somewhere on the beam, but you put that beam in bending, we're still gonna have those longitudinal shear forces, and they're not necessarily only on that horizontal portion within the beam, but they're also on the vertical face of that beam, right? So as long as that beam is in bending, you're going to have stresses within the beam, not only on that front cross-sectional face, but also longitudinally, and not for the longitudinal force or stress, not only on a horizontal plane, but also on a vertical plane, right? So that's the point I was trying to make.
Okay.
Right.